This is project 4, video number 3, the one in which we put the finishing touches and the documentation into it. I got to title the plot. I go to title. And I'm making a graph of, let's see, acceleration, magnitude of translational acceleration. I just call it magnitude of acceleration versus distance out from the center. I think I'll try it like that. If that proves to be too long, we'll change it. And then X label. Obviously, titles should vary a little bit, so there's a little bit of freedom in there, but you want to make sure you get the whole idea. That's I call it distance from center of disk. So what I've been calling R. Oh, and that has got to be in meters, and I better be very careful about the square brackets because that's mentioned twice in a handout. Make sure your axis titles include units within square brackets, not parentheses. Okay, I got a square bracket there, not parentheses. So that looks good. And then Y label. Magnitude. Oops. Magnitude of centripetal of translational. That's what I want. Translational acceleration. That's in meters per seconds squared. Semicolon. Let's see how that looks. Control S. Let's try running it. Take a look at the figure. Magnitude of acceleration versus distance from center of disk. Magnitude of translational acceleration in meters per second squared. Distance from the center of the disk. I don't like the fact that this is running beyond the height of the graph, so I think I'll just call that acceleration. Try it again. Magnitude of acceleration in meters per second squared. I like the way it puts it to it. There's a subscript, even though I use the hat as my superscript character. I hope I said superscript. Distance from the center of disk in meters. Magnitude of acceleration meters per second squared. Alright, I think that looks good. Yeah, we gotta start worrying about okay. Clearly state what the function does here. So that's your job. Write some prose about just exactly what the function does. You better mention horizontal disk with a vertical axis through its center, or words to that effect, and the fact that it creates a graph of the acceleration of a point on the disk as a function of how far out from the center of the disk it is. And then input variables. we have omega, angular velocity of the disk, and alpha, the angular acceleration of the disk, percent output variables, function returns no values. Hence there are no output variables, but I think that's self-explanatory. And then attribution, go all the way at percent attribution. Say what you used. I'd really like for you to do is tell me more or less what you did on your own, and then when you got stuck, what you really looked at video 1 for, what you actually looked at video 2 for, what you actually looked at video 3 for, as opposed to some generic statement. I used video 1 to help with the pencil and paper part, video 2 to help with the coding, video 3 for the documentation and final touches. Tell me where you got stuck. You should actually be able to do this one completely on your own, and I'm hoping that mostly you say I used no outside resources to carry out the project, but I checked my work using the videos provided by Professor Schneck. You don't have to, if you didn't really use them except to check your work, you don't have to single them out one by one like you do if you're describing what you actually used it for, what you got stuck on, and how the video got you out of that, or what part of the video you used to get unstuck. Okay, I think this thing is actually done. I'm going to save it, run it. Alright, so giving me the same results as before. Make sure it works with different values. We go -25 and 13. Well, let's see what we get there. Now, we were expecting it would always be positive slope passing through the origin because the minus sign goes away as a result of squaring, or in this case, raised to the 4th power. And yeah, we're just getting much bigger values for a given distance out from the center of the disk. It's looking good. Make sure it works with alright, I call that 1.5 and minus, let's say, 18. I haven't checked the values, but I should expect it to look the same, just different values at the end. So yeah, I think it looks like it's working. So let's go through the checklist and make sure I've got all the little pieces for the pencil and paper part. A complete algebraic solution. I feel I've got that. That's yeah, up to A is equal to is my algebraic solution. Evaluation of the algebraic solution needed to determine the test case results. That was exactly what I did here. The test case was omega is 5 radians per second, alpha is 12 radians per second squared, and r is 0.5 meters in 1 meter. And I've evaluated it at both places, the algebraic result at both places. An outline of the steps the program will carry out. Right there, there's my program outline. Would be nice to title it, but I'll have to accept it without that. I think I'll accept it without that. So code outline. So this is essentially a program written in, they call it pseudocode. Alright. As for the program, 1 point for a reasonable attempt at writing it. I certainly did that. It's got to be a .m file. I saved mine as a .m file, so we're good there. 1 point for a program that works properly. I'd say it does what it's supposed to do. Let's make sure I'm not printing anything to the screen. That's cool. Nothing being printed to the screen. Doesn't really matter whether I put a semicolon there or not, but specifically says with a semicolon there, so yeah. On this one, sometimes it does matter. If you get return values, it matters. Oh, you must have your name in every .m file. Without the name, you don't get credit for it. So, percent by Jeffrey Schnick. You make sure you put your name in there. And good thing I used the checklist. Code must be documented. A comment starting on the first line after the function statement stating what the function does. And another set of comments, so left out a word in your handout, but you should be able to figure that out. And another set of comments providing a list of arguments of the function, the input variables, with, beside each argument, a statement of what that variable is. Okay, I call them input variables, which they said was okay too, but yeah, I got my list of input variables and what each one is. This one should return no value, stating right in fact that your function returns no value. Oh, values, this function returns no values. Not very creative, but get the job done. For the case of a function that includes segments that are not self-explanatory. Okay, self-explanatory. Here's the evaluation of an expression for the magnitude of the acceleration, which hopefully you've described up there and clearly say what the function does. So, and then plot it. Oh, the lin space, it's pretty clear. Initializing r, the distance out from the center. I'm going to say that. From center of disk. Okay. And then mag. A is mag. Excel of point on disk. Alrighty. I want to read the first one so I can make it a little shorter. Is distance a point on disk from center of disk? Nope, that's good. So I'd say it's well documented at this stage in terms of anything that folks might not know what's going on. So let's see what else we got. Explain the purpose of these segments. Okay, you must provide attribution in your main function. You must include a comment giving attribution to whatever resources you used. So I didn't use any, but you say what resources. So obviously you can't copy this line. Both this line and this line are prose that you have to make up. You must provide any main function. You must include a comment giving attribution to whatever resources you used to write. In particular, if you watch the video, make sure you say so. And then I asked you specifically in the video to tell me where you got stuck and what part of the video you used to get unstuck, rather than just giving me generic descriptions. Although, in one sense, I'm hoping for generic descriptions that, like you say, is I didn't use any resources in creating the pencil and paper solution or writing the code or doing the documentation, but I did use the videos to check my work. Or words to that effect. Preferably words to that effect, not my words. And obviously, if you just say what resources you use, that won't work. Okay, and then finally, for any case in which your function produces one or more graphs, each graph must be titled. Title: magnitude of acceleration versus distance from center of disk. Check. Each axis must be titled with what is being plotted along that axis, and in square brackets, the units of what is being plotted. Okay, x-axis, distance from center of disk, and units of meters, check, in square brackets. Y-axis, magnitude of acceleration, in meters per second squared, in square brackets, check. And there must be an appropriate set of tick marks labeled with values on each axis, tick marks with values on both axes. I think we're in good shape. So let's call that a wrap for project 4, video number 3.